Okay, let's begin. It's a pleasure to present you Günther Wuchterl from the Thüringer Landessternwarte, or better known as Tautenburg Observatory, who is here today to give us an overview about the exoplanet part of CoRoT, where you, as you likely know, will be a congress or meeting, better said, next week, about 90 participants from the whole CoRoT mission, from both exoplanets and astroseismology, which is the other part of the mission. Well, Günther made his PhD in Vienna in 1995 and has really been an ingrained theorist. But more or less with the beginning of the CoRoT mission, he got aware that theory only might not be able to live on its own, and sometimes we need some observational input also. And I think he's provided a very valuable contribution, connecting our findings in CoRoT with his models, which is his specialty, which is the development of hot gas planets. So, I'm looking forward.
Also, like in the sky, and in the sky at the moment. Oh. So, as you know, this as any astronomer, I think my heart, as any astronomer's heart, my heart is in the sky. So, in the sky at the moment, there's a comet. So, as everybody's going to show the best comet pictures at the moment, you see here the comet and the moon. So, I'll give you a little bit of time before I give you the hint. You see, it's not easy. It's not, I have to confess, it's not from this island. It's from the neighboring island, where friends of mine, they are astrophotographers. They came essentially for the comet, to catch the comet on La Palma. And this is from about, I think it's 1,300 meters height. And I think you still didn't find the comet. You don't look happy. So I think you still didn't find the comet. So I give you a little bit of resolution. Okay. And I give you the hint now. You'll see the comet. But it's not the comet alone. It's the rendezvous of the comet with the moon. And if you ever wanted to see how a one-day-old moon looks like, you see it here in the clouds. I like the picture. I didn't want to I wanted to share it with you. So. Okay, but well, you know, there was the big shock for all theorists in exosolar planets, that the first exosolar planets was not like the theorists had imagined. It was not at all like it. So in 1995, I changed my life. I said, I cannot continue anymore like I did before, with all these theorists working on Jupiter and so on. And part of this total grand tech is a recent expression people like. I thought we have to characterize planets in a way that can help theory. And at the moment, I think the transit missions are the way to go forward with quantitative information about the bulk properties of planets. So I thought this is going to happen. I'm going to try to help. So I embarked on a vessel, on the CoRoT spacecraft, to help with that. And I thought the observers, they know the sky very well. And they know exactly what to do. And it's wonderful to see this expertise. But they have one problem. They only believe what they see. So what they did not discover yet, it's hard to believe for them. So I thought it's good to become a pathfinder with what was known for the theory of the solar system formation, or the exoplanet. So I'm a kind of advisor, a pathfinder for the unknown. That's my role in the CoRoT program. So many people are there, and it's a French-led mission with important contribution. The first country to join the CoRoT effort, I think, was Austria. I have to emphasize this. So then there were further and further contribution, and there's a European Space Agency contribution, and I'm here for the German Space Agency's participation in the CoRoT mission. So in every agency contributes something. The German contribution is the onboard software. So CoRoT has a particular mode of observation. It has been designed originally for seismology, and then Jean Schneider, I think, and Alain Léger realized we can make it into a planet hunter easily, a posteriori, and by that make it more interesting so that it would be launched. That has two consequences. First, it has not done everything to optimize for a planet hunter. And second, we share the spacecraft with the seismologist, so to say. So it's like you have, like in the old days when in every household there was only one television and you had to decide which program to watch. It is with the CoRoT spacecraft. It can only look to one direction, and you have to find a compromise between a seismological target, which is a bright star, and a good field for planet hunting, which means many stars. And there are further constraints that you see here. There are two circles, and these two circles are the two eyes of CoRoT. They come from the construction of the mission to avoid stray light and to be able to look in a direction for as long time as possible, and at the same moment get into an orbit that is relatively cheap, a polar 900 kilometer orbit around the Earth. There are compromises, and these compromises they result in two circles in blue and green here, and these two circles are the two directions CoRoT can point to. And it's a compromise between looking to the celestial equator and looking into a place with lots of stars, and that's the galactic plane. And as a consequence of that, we have also a seasonal schedule. About 150 days you can look in one direction, you stare at the same time, same direction. But then the Earth behind you that you circle on the polar orbit moves around the sun, and in consequence the sun starts rising as seen from CoRoT. So at some point it comes too close to the direction the spacecraft is looking, and in that moment you turn the spacecraft in the opposite direction and continue observations like that. So this gives you this circle, yeah. And in the meantime you can point to an intermediate direction. It gives the seasonal circle of the CoRoT observations, with runs of maximum of 150 days in one direction and short runs in between. So this is the sky in the CoRoT eye. Now you see every circle and the roundish graph is inside these two CoRoT eyes, and it gives you the number of stars and also a few of the extinction in these fields suitable for planet hunting. So I think this is a near-infrared image in this yellowish orange colors. So we look into directions with quite substantial extinctions in the galaxy and also quite a high number of stars. And the color-coded graph gives for the two directions the number of stars suitable for planet hunting. So it's number of dwarf stars in the field that have been mapped out by preparatory observations. So you see the stellar density about 5 is a density between close to 0 to 500. I think it's per 0.7 times 0.7 degree star. So for about 0.7 degree, you get the 500 stars where you expect it's good for planet hunting. So this is, so to say, to show you how is the satellite doing in terms of a proxy for the noise you expect. And you see from the launch date, the number of months, and you see these error bars and the point in this graph, and this point gives you the actual signal to noise in units of the theoretical signal to noise, or the photon noise. And the range, the error bar, gives you the different situations that you find on different targets. Not in all targets, the dominating noise source is the noise. In some stars, the dominating noise source is the activity of the star. So you always have a range of this noise, and you see this the nominal value slowly decreases as is expected from the aging of the CCD. It's about an aging of about a few percent per year. And there is a, so to say, that's the statistical way of looking at this. And then in the lower right, the two color coded clouds of points are two light curves. And these two light curves are light curves of the same object observed first in 2008, and then, because it was partly in a field overlap, reobserved in 2010. So you can look with your eye to look at the noise characteristics of these eclipsing binary stars to see the quality of the light curves is very similar after the years. So the spacecraft is in good shape, or I should say was in good shape. What you hear here is essentially the status of CoRoT work as of last summer. All the news you will hear next week. And here is a summary of the, so to say, the primary performance for planet hunting that CoRoT has. It's the detections in terms of the relative decrease of a certain feature. In the best case, it's a planet transit. So you see on the abscissa, you see the number of such transits that you observe. So if it's a planet, every time the planet goes around, you observe one transit. And if you observe a one-day orbit planet, you can observe 100 such transits in 100 days. So here you have single transits, single signals, I should be precise, 10 signals, 100 signals, and some of the signals are shorter than a day, and some of the runs are longer than 150 days. So the more the signal repeats, the lower the signal can be detected. That's visible here. And then here is the logarithm of the relative change in flux in percent. So this is 10 to the minus 2%. So this is 10 to the minus 4. So you see, if you have enough transits, 100 transits or so, a signal of 10 to the minus 4 can be detected. And the color code shows you on which type of star you detect this. It gives you the magnitude. So you see, these signals can be most easily detected on bright stars, which is not a surprise. So CoRoT can go into the domain of terrestrial planets for short periods and relatively bright stars. Most of the detections are here at the log value of 0, so that's a 1% decrease. That would be a typical Jupiter in front of a G4. Here are these 3,000 detections, and the detection is just a signal, and it can be everything. Even the dead star passing the star in a repetitive way, you don't know a priori what it is. It just means you have a signal that you can clearly detect the spacecraft. See this? So after a process that I will illustrate in the following, you can verify that the signal actually belongs So a planet is of planetary nature, and here you see the CoRoT family portrait as of last August. So these are the 23 confirmed companions, I should say, including about 2 or 3 companions that are in the brown dwarf planet transition area. If you look at the mass, so that's gives you an overview of the signal. In all cases, you see a constant signal with the noise in gray, and then you see the events, the transit across the surface of the star, and then the egress when the star goes back to the nominal brightness. So in CoRoT, it's the custom. Actually, I would call it almost a policy. Yeah? It's a policy to determine the mass of the planet prior to publishing. So I think it was very important because CoRoT was the first space transit mission, and the goal was so high to have a very careful validation of what you see as a signal. There are a lot of parasitic signals that we will discuss in a second or in a minute, but one has to be careful. And what the CoRoT team does, and this is a large effort, is to determine the mass of a companion that is detected through the transit signal. And that involves a sometimes very large radial velocity follow-up program. And this radial velocity follow-up program, you can see the effort a little bit on the number of points on each graph. Each of these graphs is a radial velocity study for one of the candidates that I've shown you, and each point is a high-precision radial velocity measurement to get the orbit that you see as a sinusoidal or typically Keplerian line fitted through this point. So in some cases, for CoRoT 7, for example, there is 100 of radial velocity measurements, and next week maybe you will see studies with 200 or more radial velocity measurements to come up with the mass of one single candidate. So it's an enormous follow-up effort to make sure the planet is not only identified by one property, its geometric size that covers the surface of the star, but by a second property that is the mass measured via its acceleration on the star. Needs a battery. So I talked about signals. I got it. So I talked about signals and planets and the masses of planets. And this is a very short summary of why a huge effort is necessary to make sure a signal or a candidate in the terminology is a planet. You see, there is the nominal situation of a planet, the nominal signal as you like it to be, with only the planet involved. But also a binary star where the secondary, the companion doesn't fully cover the surface, would induce a similar signal. And an even nastier wrong signal, a false positive, so to say, would be an eclipsing binary in the background of the star, which mimics a small planet on the star. And so to say, if you want to go to the most extreme, and this was necessary for CoRoT 7b and is necessary in all cases when you have very small planets. If you find a very small planet, Earth size, then the parasiting signal could be a planet itself, because you can put a star with a Jupiter orbiting these stars behind your actual target star that mimics a small planet at your front star, so to say. So you can imagine that it's not easy to distinguish between those, and CoRoT put a lot of effort to very carefully do this. And you see the number of nights put into these programs. And Hans Steg here at IAC, so Mr. Photometry, so to say, of this program. The first check is that if you look at the star with CoRoT, you see not only these stars, but you see neighboring stars. So the first check is photometrically look at this place again, typically from this mountain here, and make sure there's not a weak star on the side of the target that mimics the transit signal. Yeah? So it's not the planet on the star you believe, but there's a faint star nearby that mimics the signal, and that can be done with a photometric telescope. The reason why this is necessary is that the CoRoT point spread function is defocused. It's a very old technique. Karl Schwarzschild pioneered actually this technique in Vienna by defocusing the Pleiades to spread the light over larger area on the detector to in the end get more dynamic range for the measurement, and this is done for CoRoT. But there is a cost for defocusing and spreading the signal, and that is your aperture for the photometry gets large. And what you see here is the CoRoT PSF and all the parasitic, so to say, the confusing stars near this PSF. So you want to make sure the planet, the signal comes from where you think the signal comes. So you first increase, so to say, with natural seeing, you increase the resolution, natural seeing observations. Make sure all the stars that are near the target stay constant enough not to exclude that they are being able to induce the signal that you have picked up with CoRoT. And you can imagine the fainter the star, the smaller the signal that it can mimic. And in some cases, you have to go very close to the star and to repeat this investigation with adaptive optics observation to get a conclusive result and exclude any other interpretation of the signal than the planet. So the entire story of this making sure it's a planet is, in my opinion, I think I can say this because I'm a theorist, but in my opinion, it's kind of a general piece of art where almost all astronomy, all stellar and planetary astronomy contributes, and it brings many evidences, a lot of different evidence together to finally exclude all the other interpretations at high confidence. And you see here some of them put together for the case of CoRoT 22b. So that's the telescopes that are used for that. If you contribute to the CoRoT effort and your telescope is not there, please visit me after the talk. So I can show you my home telescope here, the 2-meter Karl Schwarzschild Observatory in Tautenburg. So say, the planet is made on the ground, is the bottom line. You get a hint, a candidate from the satellites to know where you put your efforts, to which targets to direct your efforts. But the planetary nature is made on the ground. So the August 2012 status, you get the August 2012 status because if I take all the news from the team, next week would be a boring week, but I recommend if you want, there will be a few very nice results, I think, next week. I can only give you the August 2012 status. To see the newest news, you have to meet the mission PI and Magali and the people who actually did the work, not the people who comment the work like I. So, operation last summer was for about 2,000 days. 23 so-called runs, which means one pointing in one direction. with durations of 20 to 150 days. So the longest coverage is 150 days, not like Kepler that will go to 5 years or as long as it can. We have 155,000 stars observed, and I'm going to break my promise because by now you can calculate that CoRoT has observed more stars than Kepler. So I have to make this point here. There are about 4,000 transits detected, and then you have to make a kind of ranking of what is a good candidate, what's a bad candidate, and 545 candidates were selected to be worth the huge follow-up effort as a trade-off. In the beginning, you think you follow every candidate, yeah? Because it might turn up as a planet, but then you discover you're not going to survive this procedure because it's so much work. So there is a selection for what cases can be resolved with an effort that can be justified, in particular, where you can convince OPC members that this is worth all the observation time. 300 have been solved. Here is some indication of what they are. There are some left, about the same number left. No, 160 left. And so far there are 25 planets found. So this Claire Moutot put this together, this graph, to show what is the status of this process of the planet verification. And you immediately discover, if you look at the magnitude scale at the abscissa, you see the bright ones are all done. Yeah? And as you go fainter, more than half are not done. So you have the total number. The blue is where there is still work ongoing, and the others are, so to say, put to the files, either solved or some cannot be solved. Will not be conclusively, cannot be easily solved. So this is a distribution of solved and unsolved cases. Yeah? This huge part of the pie chart is called diluted, and that is some extra thing contributing to the photometric measurements. 70% are planets, and a quarter are the spectroscopic binaries. So it's a true signal, but the wrong type of object from behind. We have a fairly complete ability to detect Jupiters. You have seen this in the signal. Kepler has a fairly complete ability to check hot Jupiters. CoRoT is not, so to say, complete for the very small sizes, but Kepler is complete for the smaller sizes. But for the Jupiters, for the large planets, you can compare the signals of CoRoT to the signals from Kepler, and that's an effort that has been done. So we look at the giant detections and the follow-up for Kepler and CoRoT. Remember, it's a giant planet, so if you do a radial velocity follow-up, it's relatively cheap, because the gravity signal, the radial velocity signal is large, so it can be easily done. And by that, you so to say, you compare the 27 centimeter CoRoT to the 1 meter Kepler in a photometric domain where it doesn't make a difference. So both should have similar performance. So CoRoT is now at about the same number of stars, a little more than Kepler, but about the same. And for giant planets that cause a signal of larger than 0.3%, we have a match count of CoRoT to Kepler that is given here, so 241 to to 54 candidates. So you have detected the signal with confidence. If you do the follow-up in the same way for the Kepler and CoRoT candidates, you end up with giant planets, so which is now a signal that has a detected gravity measurement, so the planet actually has a mass. You get 19 Kepler planets and 23 CoRoT giant planets. So you see I think we are observing the same sky, the same candidates, we get the same yield. So the parasitic signals of Kepler and CoRoT are comparable, the follow-up efficiency is comparable. And you can also, from that, estimate let's say, a false alarm probability. If you have a candidate that you think is a good candidate because you have done some sanity checks and so on, you still have a 35% rate of discovering that it is not a planet when you do the radial velocity gravity measurement. And that seems to be the same for Kepler and CoRoT, according to this study by Wuchterl and company. Essentially what they did, do the CoRoT follow-up procedures for the Kepler signals. So for the giant planets, we observe the same sky with the same efficiency, same errors. Given the fact that the approaches are very, very different, the approaches are very different. I have no time to discuss this in detail, but the philosophies between Kepler and CoRoT are very different. For example, in Kepler, there's one, so to say, standard pipeline to come up with candidates. CoRoT, so to say, the more European approach, every participant, almost every participant, had his own pipeline, which led to a diversity of methods with mutual learning and improving procedures. So concepts are different. First, you try to put all in one, all knowledge into one. The other is try different approaches. And this comes up with very comparable results. I think it's a very, very great success that we have this agreement. So highlights, what is it all about? What are the results? CoRoT 2b is, so to say, the young, impossible planet. If you believe in any standard approach to planet formation and evolution, this object cannot exist with these properties. And this is the real CoRoT 3b is, yeah, what is it? I have a bet going on about the final classification of CoRoT 3b, whether it will be a planet or a brown dwarf. I think it's 22 Jupiter masses, so you can start the discussion and put your bets. It's a singular object in an astrophysically previously unsampled domain. If you look at the radius mass diagram of any object, it's a unique place. We have a couple of brown dwarfs, so we know brown dwarf radii from transit measurements. We have CoRoT 9b, which for the first time proved that our theory is good of something. Because before CoRoT 9, all the Jupiters that were found were hot Jupiters, and they have what is called the radius anomaly. They are inflated, they are too large, their density is too low. And there was, every theorist, of course, assumed there's something wrong with being close to a star. Nobody had thought about being close to a star for theory of giant planets. So there was something wrong. Yeah? But there was no proof. CoRoT 9b is the proof that if you do standard theory in a 100-day orbit, everything's good. Theory is useful for something. A Jupiter has a Jupiter radius if it's far enough away from the star. That's this CoRoT 9b story. CoRoT 7b is, I think, the heritage planet of the CoRoT mission, because you might not be so aware how big the problems of planet formation are in the first step when you produce the planetesimals. The planetesimals, 10-kilometer sized building blocks for planets, where you can see the traces everywhere in the solar system. I showed you another one. I showed you another one earlier in the beginning of the talks. They are everywhere. They exist. But theory had a problem to prove that they can be formed not only in the solar system, but in general. It was completely unclear if the planetesimal formation process could be understood, and thus whether it could work under general conditions. So this is, in my opinion, the theoretical bottleneck for answering questions whether solar systems like ours are common or a terrestrial planet like ours are common. It's the planetesimal formation. It's not understood. But now, given we have a terrestrial planet, a high-density planet, which is certainly made of rock mostly, rocky elements, heavy elements, there must be a very general way to form a planetesimal, because otherwise you would not form a terrestrial planet. So I think this is going to be the heritage. The first proof that the channel to terrestrial planets is a wide one is with CoRoT 7b. Yeah, the challenge of the theory for CoRoT 2b. Here you get a summary of, so to say, the primary CoRoT result, which is the mass versus radius. You have on the abscissa the radius in Jupiter units, and on the ordinate you have the mass in Jupiter masses plotted logarithmically. And what you see that there is an overlap with the one Jupiter mass, one Jupiter radius population that you get from the ground. But if you look to the lower left, where you go to 1/10 of a Jupiter mass, 1/100 of a Jupiter mass, and 1/10 of a Jupiter radius, you have a tail of planets that extends to that in this diagram. And on the end of the tail, CoRoT 7b has this very small planet. So we have contributed very small planets, very low mass planets, and the density range of known planets or planetary-like structures has been extended by the CoRoT sample from 0.3 to 30. Compare that to the solar system. We have now about a good 2 orders of magnitudes in planetary densities. These are upper limits, I think, in mass. I think it's Roy's planet, right? You must recognize it. Can you confirm this? This is the green Roy planet. So this is the same exoplanet harvest plotted in the semi-major axis mass diagram. Now both axes are logarithmic, and you see there is a wide range in semi-major axes that mostly come from radial velocity searches, and all the transit planets, which are in orange in this plot, and the CoRoT discoveries, which are in red in this plot, they tend to be short periods. And you see that at this time, CoRoT 9b with 100 days was leaning towards this extension of the radial velocity planet. So, but most of the planets are still short period planets. This is a double reason. First, it's much more probable to discover a short period planet by transit, and second, it's much easier to determine its mass, because if the planet is close to the star, its gravity, because of the 1/r square law, is larger and therefore easily to detect. The same thing in the radius semi-major. It's again in Jupiter units. And you see how Corona B stands out, and that there is now, so to say, a link between high density terrestrial type planets and the inflated Jupiters. I should re-emphasize, if you look at the radio scale, the median, the typical value of a Jupiter-like planet is much larger than Jupiter. This is radius. It's not a weak effect. The radius anomaly is a strong effect. It's very present for planets close in and disappears if you move away from the star. So the issue of planetary systems, you know that Kepler discovers lots of planets in planetary systems. So people try to discuss where are the systems in CoRoT. And the short answer seems to be that because of the small spacecraft and the photometric accuracy limits on most stars, we only occasionally discover planetary systems. When they are unfavorable, that means bright stars. Yeah? And one is the CoRoT 7 system, where you will hear more next next week, and the other one is the CoRoT 24 system, which is Roy Alonso's baby. The CoRoT 7 discovery is a very strange planet indeed, and I just briefly show you this graph here. Extreme temperatures, maybe molten rock, but at the same time, because there's a day-night, very strong day-night shift, very likely there's no atmosphere. Extreme temperature differences cannot be wiped out by atmospheric motion. So it's a very extreme type of planet. Just to give you a flavor of how extreme, the star, as seen from CoRoT 7, is so big that both poles are in permanent sunlight. And there's a huge area around both poles, which is permanently sunlit because the star always shines on both poles. This is the Alonso system again, 2 planets. So we can detect planetary systems. The CoRoT 7 system is a radial velocity detected system. So this is the first CoRoT detected planetary system. This is an effort to find out whether we are good in detecting the small planets or whether there is anything that we are doing wrong when detecting small planets. And this test where you insert artificial planets into real CoRoT light curve shows that we should detect the small planets, but we haven't yet. And very likely, when we better understand the light curves, we will come up with more, and the spacecraft will come up with more Neptunes that are so far looks like they are under-detected. So this is the last year's news, CoRoT 25 and CoRoT 26b. This is the last published detections. This is a very interesting category because if you remember the diagrams, there are lots of Jupiters and lots of very small planets, also from Kepler, but the Saturns are of a rare kind. You might remember that there are a lot of Neptunes also expected from radial velocity searches, but the Saturns are relatively rare. So this is a particularly valuable addition to the planet family. And they are particularly useful for theory. I cannot go into detail, but you can imagine that this is the transition from envelope-dominated planets to core-dominated planets. So they are very, very interesting from the internal structure. Here you see the light curves and radial velocity measurements. And I'm sure you're going to hear more from Roy next week. And this is how they fit into this place. And you see there is this big armada of planets on the right at roughly a Jupiter mass. And here there is the planetary, how do you call it? I think it's a flood. It's a flood of small planets, a flood of Neptunes on the left side. And this is underpopulated, this diagram, because most of the discovered planets of Kepler have no mass. So they cannot be put into this diagram with mass and radius. So this is very underpopulated. So you have these two crowds, and in between there is this uncharted land in the mass radius diagram. So I think my time is nearing the end. So I want to give you as a summary that this is only, what we see now is only the tip of the iceberg of what CoRoT will bring. There are lots of things to be done, and as usually the full harvest will come when we had enough time to understand how to do the follow-up. And I should say, in the end, the community will decide about the harvest of both CoRoT and Kepler, because to harvest the astrophysical information, to harvest the density of the planet, the mass of the planet, a considerable investment is necessary. But we have to be very clear, CoRoT and Kepler for a long time to come will be the only window to exosolar planets that can provide both the radius by space-grade photometry and the mass by ground-based polar observations. So I think we are going to have more surprises that were the start of my engagement with CoRoT.
Yeah, thanks a lot for this interesting talk. Now we have some time for questions. Does anyone have? So may I ask one? So you said this is the tip of the data iceberg. What is now what would you say could be the main discovery next?
I could say what is the next discovery, but then the people who really do the work would hate me. I think if you want to see the next story, you have to come next week. I can tell you my guesses without systems. I've shown you that systems are within the reach of CoRoT, so systems will be there. With more smaller planets, I'm sure, and because of the double nature of CoRoT, the seismologists sit on the same spacecraft, and I think the combination will bring very, very good results. And I've shown you a few interesting riddles which rely to chronology. And actually, I've told you that the physics cannot be corrected to use, and I was really responsible about it. So I think you can. If you ask me for the discovery, I cannot answer this. You have to come next week.
Any other questions?
This is a bad idea question. You know that one of the great successes of Kepler has been to have this systems where the star is also pulsating. I mean, they have a stereosismology at the same time on transit. Do you think that this will be a possibility also for any of the CoRoT candidates?
I think so. I might even know. I think there's actually I might be confused, but I think there are pulsating stars that are on the candidate list. I think of the published planet, Hans will know this. Of the published planet, there is no pulsating stars. You have there are spot variations, very famous light curves, but from the published ones there are no pulsating stars here.
Okay, I just want to say that next before week talks will be on the web, retransmitted to our website. So anyone who talks to in this Olivia password is January, not more. Anyway, you can ask me about it in the conference website. Well, thank you very much.
Just the final word. if there's any theories that wants to learn about how to understand this, see me in the cafeteria.
Well, thanks. We're looking forward to your announcing next week.